Antiderivatives. Our objective is to find the antiderivative of a function. Remember that when we take the derivative of a function we might call f, we use the notation f prime often. Well, today we're going to talk about going backwards, taking the antiderivative. Remember the prefix anti means against. So the antiderivative of f prime means against the derivative or opposite to, going backwards, yielding the original function called f. Well, the notation we use for when we start with the function lowercase f is uppercase f. The function capital F is called an antiderivative of the function f if capital F prime of x equals lowercase f of x for all x in the domain of f. So we think about it like this. If we have the function f and we take its derivative, the notation will be lowercase f prime, the derivative of lowercase f. If we're going backwards from f, or taking the antiderivative, that would be uppercase f. The general form of an antiderivative is when the function capital F is an antiderivative of lowercase f, defined on an interval I. Any other antiderivative of f has the form capital F of x plus c, where c is any arbitrary constant. Let's think of it like this. If I ask to take the derivative with respect to x, I'll use this notation d dx, of the function x squared plus 5. What do we get? The derivative of x squared is 2x, and the derivative of 5 is 0. 2x plus 0 is just 2x. How about the derivative with respect to x of x squared minus 10? I've only changed the constant here. What do I get? The derivative of x squared is 2x, and the derivative of negative 10 is 0, so I still end up with 2x. I'm going to change the constant again, the derivative with respect to x of x squared plus 100. Again, the derivative of x squared is 2x, and the derivative of positive 100 is 0, so I still end up with 2x. It does not matter what that constant is. I'm going to call it c for any general arbitrary constant. That constant will always have the derivative of 0, no matter what it is, 100, negative 10, positive 5, it can be any arbitrary constant. That constant's derivative is 0. So the derivative will still be just 2x. So when I'm thinking about taking the antiderivative of 2x, it's going to be, what does the variable expression have to look like, but then plus some arbitrary constant, because the derivative of any constant is 0. So the general form of an antiderivative is always capital F of x plus c. Thinking backwards to what could the original function be plus a constant every time. Now let's talk about some rules that are commonly used, like when we take derivatives, such as the sum and difference rule and the constant multiple rule. Remember how in each of these I did the derivative of one term at a time. First the derivative of x squared, then the derivative of 5, and then added the results together. Similarly, when we take the antiderivative, we can also do it in pieces. So if capital F sub 1 and capital F sub 2 are antiderivatives of lowercase f sub 1 and f sub 2 respectively, then capital F sub 1 plus or minus capital F sub 2 is an antiderivative of the sum or difference of lowercase f sub 1 and f sub 2. Similarly, the constant multiple rule. If k is a real number, and if capital F is an antiderivative of lowercase f, then the constant multiple times f is an antiderivative of the constant multiple times lowercase f. Just like when we take derivatives, the constant multiple hangs out and gets multiplied to our derivative. Now it hangs out and gets multiplied to our antiderivative. Now when I take antiderivatives, what I like to try to ask myself is, what did the original function have to be that would give me this as a derivative? In order to do this, it's very important that we know all of our derivative rules. Here's a quick reference list of functions and their antiderivatives based on the derivatives that you know. For example, because the derivative of a constant is 0, the antiderivative of 0 is a constant. And because the derivative of x is 1, the antiderivative of 1 is x, plus a constant. Notice that constant each and every time we take an antiderivative. Similarly, using the power rule, if we think about taking the derivative of something such as x to the fifth, the power rule says multiply by the exponent, so the 5 multiplies out in front, and then subtract 1 from the exponent. So to go backwards, taking the antiderivative of the function, I'm going to do the opposite, which is add 1 to the exponent first, and then divide by the new exponent instead of the subtract 1 and multiply by that previous exponent, or rather first multiply by the exponent and then subtract 1. So we want to think of going backwards, or what did the original function have to be to give me this as its derivative? Thus, it's important you make sure you've memorized all of your derivative rules. Let's take a look at some examples. Find all the antiderivatives of each function. Now, when they say all, we remember that that's because there is a general form of the antiderivative that includes a plus c, where c could be an infinite amount of constants. Number 1, f of x equals x to the fifth plus cubed root of x squared minus 3e to the x plus 2 secant x tangent x. Now, just like when we take derivatives, sometimes it's helpful if we do some rewriting when it's necessary, and we do need to rewrite when we have a radical expression. So rewriting this, f of x equals x to the fifth is fine how it is, but the radical we want written in exponent notation. So that becomes x to the 2/3. Remember, the root is the denominator of the exponent. This one is fine, minus 3e to the x, and this one is fine, plus 2 secant x tangent x. Now we can take the antiderivative. Our notation for the antiderivative of lowercase f, capital F. Capital F of x equals. Now, thinking of my power rule done backwards. First, add 1 to the exponent. So the exponent becomes 6. Then divide by the new exponent. But it's easier in all cases if we think of it as multiplying by the reciprocal. So we'll multiply by 1/6. Next, add 1 to this exponent, but because it's in thirds, we'll add 3/3. So this becomes x to the 5/3, and instead of dividing, it's easier when we say multiply by the reciprocal, so times 3/5. Next, this 3 is a constant multiple, so using my constant multiple rule, it hangs out in front. And e to the x is the easiest because the derivative of e to the x is e to the x, so therefore the antiderivative of e to the x is e to the x. Next, plus 2 is a constant multiple, so it hangs out. And then I think about secant x tangent x. It is the derivative of what trig function? That's right, secant x. And as with all antiderivatives, I have a general constant plus c. Now this is a general antiderivative. If I can tidy it up a bit, I would. It doesn't look like I have anything to multiply, so it looks like I'm fine at this point. Number 2, g of x equals x cubed plus 2x minus 3 divided by x to the fourth. Now again, if we can rewrite it, we should. And just like when we take derivatives, if I don't need to have a quotient, I don't want to have a quotient. So let's split up this quotient. X cubed over x to the fourth plus 2x over x to the fourth minus 3 over x to the fourth. We can clean this up a bit, so now g of x can look like 1 over x plus 2 over x cubed minus 3 over x to the fourth. Now I still have quotients, I still have x's in the denominator. This 1 over x, I don't want to bring that up as x to the negative 1. If I go back to my reference list, this one is very important to remember, that the antiderivative of x to the negative 1, or 1 over x, is the natural log of the absolute value of x. Remember that when we take the derivative of the natural log of the absolute value of x, we get 1 over x. So when I see 1 over x, I'm going to leave it as 1 over x, and therefore I can take the antiderivative to get natural log of the absolute value of x. So this one will stay as 1 over x while I rewrite the others so I can use my power rule. G of x equals 1 over x plus 2 times, I bring the x cubed up and it becomes x to the negative 3 minus 3 times, I bring x to the fourth up and it becomes x to the negative 4. Now I'm ready to take my antiderivative. I use my uppercase G to symbolize the antiderivative of lowercase g. I remember that 1 over x is antiderivative is natural log of absolute value of x, plus 2 is a constant multiple, so that hangs out in front while I do my backwards power rule. Add 1 to the exponent makes x to the negative 2. Notice I left some space in front because I'm going to be multiplying by the reciprocal of the new exponent, which is negative 1/2. Next, minus 3, constant multiple, and then I can use my power rule again. Add 1 to the exponent makes x to the negative 3, leave some space so I can multiply by the reciprocal of my new exponent, negative 1/3. Now we can tidy this up a bit. Capital G of x equals natural log of absolute value of x. 2 divided by 2 is 1, so this is negative x to the negative 2. 3 divided by 3 is 1. Negative times negative is positive 1, so plus x to the negative 3. And oops, what did I forget in that first line for the antiderivative? Always plus c, plus that arbitrary constant. Now this is a valid answer. This is an antiderivative, but I generally don't want to leave negative exponents. So let's do one more step to clean it up. Natural log absolute value of x minus 1 over x squared plus 1 over x cubed plus c. And there we have it.